This project is a quick kind of a visual overview of things in the universe, from planets, comets, stars. If you're somebody that likes to visualize things and not just read about them, this project will help you out a lot. I'm one of those people, so this really helped me a lot. What you're going to need is 3 pieces of black paper, 1, 2, 3, kind of attached together like this. Okay, it's going to be a very long mural. Right, and then you're going to need some kind of a gel pen. This one's going to be silver. You can get white. You got to be careful because some of the colored gel pens will write on top of here real nicely and show up, and others kind of just soak in. So you might take a couple tries to get a gel pen that works, but I'm going to use silver. It seems to work pretty well. If you don't have black paper and gel pens, you could do this on white paper just with a pencil or pen. White paper would work fine too. Black's just a little dramatic, that's all. So now we've zoomed in on the first piece of paper here, and the first thing we want to put in is the planets. Okay, let's put the sun right about here. Don't put it right at the very edge, just come in a little bit because we're going to put a few things going around it. Put a few rays out like that. Okay, there's our sun. And then we're going to put all the planets just like this. Now it's going to be out of scale if we really put them to scale. You want here and here and here, and then zoom would be off the paper. But we're going to kind of jam them all in here. Mercury, Venus. We'll put this up a little bit here. Now, the planets are almost never lined up in a straight line like this. Like Mercury could be here or here or here. Venus could be here, here, Earth could be here. They'd all be scattered around. But just so for convenience, we're going to put them looking like they're kind of in a straight line. Okay, Earth. Then Mars. And at this point, we're going to have to put in between Mars and our next one, Jupiter. We could go ahead and put in here a belt of asteroids. Asteroids are little chunks of rock or piles of rock. They're like flying rock piles held together by gravity, a little bit of ice. So some are teeny tiny like pebbles. Some are very large. The largest of them we can label here. The largest is called Sirius, and it's like hundreds of miles in diameter, but most of them are a bit smaller. Okay, so there's our asteroid belt. I'll go ahead and label it here. Asteroid belt. Okay, and next out we've got Jupiter, the largest. And then we have Saturn, famous for its rings. If you want to put a ring around it, you can do that. And then we've got Uranus and Neptune. Now we're not going to put Pluto on because they tell us Pluto's not a planet anymore. People still argue whether that's true or not, but we're going to put Pluto out here in a special area in a little bit. Now I want to add a few more asteroids. They're going to be near Jupiter. If Jupiter's orbit, the path it travels, if we kind of just put some imaginary dashed lines showing the path that Jupiter follows. If you made a triangle, an equilateral triangle with the Sun, Jupiter, and a point down here as the points of the triangle, that's where you'll find a little group of asteroids down here and also up here. Some people call these Trojan asteroids. And this area here is called L4, and this one down here is called L5. L stands for Lagrange, named after the mathematician who predicted these points. L1, 2, and 3 lie along this axis. L4 and L5 are at 60 degrees. 60 degrees down here. And they are stable points. You know, there's the gravity of these. Jupiter's pulling, and the sun's gravity's pulling, and this is an area where it just so happens that it's just in the right place where it doesn't get pulled in too far to either one, and things can just kind of collect. If you were here, you'd just kind of get dragged into Jupiter. But this is a stable area where asteroids can kind of float, and they ride along. They always stay in position. They ride as Jupiter moves, they move along with it like this. So these stable points are called Lagrange points. Earth has some too, actually. All the planets would have some. Earth has a couple of asteroids that ride, or at least one, and one of these has its own little Lagrange points also. But these are the more famous ones. Jupiter's larger, so it has a larger collection of asteroids. Next, we want to add moons. Now, Mercury and Venus don't have any moons. And of course, you know Earth has one moon, and we just call it the moon. Actually, the moon is the proper name for our moon, and other moons are actually satellites, but we tend to call them moons, so I'm just going to go ahead and call them moons. Mars has 2 moons. One is called Phobos, and the other is called Deimos. Jupiter has a lot of moons, but 4 really famous ones. These 4 are the ones that Galileo saw in his telescope, so sometimes they're called Galilean moons. They're called Io, Callisto, Ganymede, and Europa. Ganymede's the largest. Io is famous because it has a volcano on it. Several of them have water and ice on them. Next is Saturn's moons. The biggest one here is Titan. And another famous one is Enceladus. Enceladus has strange gas jetting out from the South Pole. It's one of the things it's known for. Uranus has a number of moons, the most famous of which are Oberon and Titania, and if you're familiar with Shakespeare, you'll recognize those names as the King and Queen of the Fairies in Midsummer Night's Dream. And someone told me that actually one of the smaller ones is named Puck. So a lot of these have names associated with classical Greek drama, and particularly Shakespeare. Neptune also has some moons, and the only one we're going to bother learning here is Triton. And Triton is interesting because it kind of goes the wrong direction. Now, everything in the solar system travels this way, pretty much counterclockwise or anti-clockwise. And we might even want to indicate Earth's orbit to remember it goes this way around the sun. And when we're looking down at the solar system, we're pretending we're looking at Earth's north pole, so the Earth is rotating this way. And the moon is going this way around the Earth. And almost all of the moons are going this way. Not all, but most are going this way. And all of the planets are orbiting like that. They're spinning counterclockwise. Except for Venus is spinning the wrong way. Venus is going this way. Even the sun rotates. It's going counterclockwise. And because the sun is going this way, the sun is rotating that way, that's considered the correct motion. It's called prograde. So all of these are going prograde, and anything that goes backwards the wrong way is called retrograde. One interesting thing is Uranus out here, it rotates this way. It's kind of tipped. So those are the two kind of oddballs of the solar system. Venus is rotating the wrong way, and Uranus is also rotating the wrong way, but in kind of a perpendicular way. Now I mentioned that everything is out of scale here. This is not a correct scale. If this was the distance between the sun and the earth, we consider as 1 astronomical unit. We measure everything against the sun to the earth distance. And Jupiter is 5 times as far, so we'd have to go 1, 2, 3, 4, 5. Jupiter would already be off the page. So we've kind of shoved everything this way. But if you'd like to know the distance that Earth is away from the sun, you can mark it on your paper if you want, is 1 astronomical unit, or AU. And Jupiter is about 5, approximately. It's point something something, but 5 is close enough. And if we go all the way out here to Neptune, at the edge here, we're all the way out to about 30 astronomical units, AU, away. So that would really be off the page. Now we're going to add a feature that is some people's favorite feature of the solar system, and that is comets. Comets come in basically 2 types. There's some that are different from this, but people tend to group them into 2 groups. One is called short period, which go not too far out. They go around the sun and out to about Jupiter, maybe a little before, maybe a little after, something like that. And then there's long period comets that really, really go far out of the solar system and back. So let's just draw a real sketchy line here. Now comets go very close to the sun and then go out. Let's draw a short period comet that goes out about a little past Jupiter and back in. Well, the shape we're drawing is an ellipse. Some comets have a more circular pattern, and some are very long ellipses. This is kind of just an average ellipse. Okay, and let's see. They go out to about, so this is going to go out to maybe, this is 5 astronomical units, so this is about maybe 6 or 7 astronomical units away. And we'll actually draw the comet right here. It's starting to form a tail. And let's draw the comet real close to the sun, like this. It has a tail streaming away from it, and the tail, you know, always goes away from the sun. So as it moves, the tail always points away from the sun, like this. Okay, so I'm going to label this short period comet. Now these still take years and years to complete this. When they come in here, they go very, very quickly. And in just a matter of weeks, they spin around the sun here and go back out, and then they spend years out here. So let's put in a long period comet. Let's see, we'll make it way out. Now we want to head way out here, way past Neptune. Oh, I want to do my other part of my ellipse down here. Way out here. We'll say that this one goes like about 35 AUs away. Let's make this Halley's Comet. Halley. Very famous comet. It comes back every 75, 76 years. And it goes all the way out past Neptune. Some go even a little bit further, but it's kind of an average long period comet. So let's make that Halley's Comet. And when it comes in here, it comes only a half astronomical unit. So half the distance between the Sun and the Earth, that's about how close it comes on this side. Now it's time to slide our paper a little bit here. We're going to go a bit beyond Neptune. When you go past Neptune, they call things out here trans-Neptunian objects. Trans meaning across or further than Neptune. So we're basically going to use most of the second sheet. The third sheet's going to be from really deep sky objects. So make sure we don't get too far there. Okay. Right after Neptune, we find something called the Kuiper belt. Now, it's a lot larger than the asteroid belt, much, much bigger. But it has sort of similar objects. There's little rocky, icy bodies. Some are small, some are very large. Okay, and this is going to be called the Kuiper belt. Things are usually named after the people that discover them. So you get some interesting names. And most of these little objects we don't have names for. But there are a couple things that live in the Kuiper belt that are pretty famous. And let's see, the Kuiper belt, you might want to put, it extends from about 30 to 50 AU, astronomical units. That's about how far it is. So that's 30 times the distance between the Sun and the Earth to 50. So it's on the order of almost the size of the whole solar system. So once again, I'm really scrunching it in here. It would have to go out much further. Okay, one of the first things you find in this area is the ever popular Pluto. Pluto is about 40 AU away at its furthest point. You can even put, Pluto has a couple little moons. You could put a couple little moons in there. One of Pluto's moons is called Charon. He was the ferryman in the Greek mythology that crossed the river, taking you to the underworld. Okay, what else is in the Kuiper belt? There are two little things. These are often called dwarf planets. Sometimes even Sirius in the asteroid belt is considered a dwarf planet. Pluto's a dwarf planet. Another one, we'll just put it down here, is called Haumea, Haumea, named after a mythological figure from, I think it is Hawaiian mythology. And there's another one, we'll just space them out. We'll put this one up here. They call it Make Make. It looks like make. And this is another mythological figure. This time it's from Pacific Island peoples. I think the people group on the Easter Islands. That's from their mythology. And then you have an area just beyond the Kuiper belt. You have an area that's still kind of the same. It has little tiny bodies floating, but it's maybe a little more sparse. I don't know if we kind of will make a dividing. There's not really a dividing line, but kind of in our mind here, just so we get it clear for how we think about it. This is called the scattered disk. And the most famous object in the scattered disk is called Eris. It's another dwarf planet, and it has a couple little moons. There's one moon there. It's about 96 astronomical units away from the Sun. The scattered disk goes from about 45 to 100 astronomical units. So you don't measure things in kilometers or miles out here generally. You measure them, they're so large, you have to go to astronomical units. Remember, 1 astronomical unit is the distance between the Sun and the Earth. So the next thing after the scattered disk is, we're just going to kind of, now there, of course there are not lines here, but just to make it clear for ourselves, you have at the edge of the scattered disk, I'll just kind of write it here, you have the end of the heliosphere. Now, to explain what the heliosphere is, we should probably go back a little bit and add one more feature here. Let's go back, look at the sun here, and make some wavy lines going out like this. The sun is constantly putting out particles. We'll call this the solar wind. Streams of all kinds of radiation and particles stream out from the sun, and they travel all the way through the solar system. And then way out here though, they start to slow down, and this, when you get out to here, you don't feel the effects of the sun very much. Let's put in another line that'll help explain this. Another little imaginary dividing line. They call it the termination shock. And you may even want to write this in. This is where the solar wind slows down. Oh, I'm going to start right here. Solar wind slows to less than speed of sound. Now that's still pretty fast. When you get out to here, it starts slowing it down. You have other particles, other, like they call it the interstellar medium, other things floating out here, and the solar wind comes out and it kind of starts buffering against here, going sideways, and it slows down. And so this thing called the termination shock is where it slows down, where it goes going below the speed of sound. And then you have a place here where it kind of ends. Once again, there's no lines in space, kind of an imaginary, there's no definite actual area. It's kind of a little bit vague here, but this is called the heliopause. And this is where you pretty much have the end of the solar wind. This is about how far the sun's effect goes. Just about to here. This is on the order of like 100 to 120 astronomical units away. Now the interesting thing is, we're going to add two little objects right here, just after these areas where the sun loses its effectiveness, after the heliopause. We're going to put two little dots here, and these are actually man-made objects. This is, put one a little bit closer, we'll call that Voyager 2, one a little further away, this is Voyager 1. These are the satellites that were sent out and launched in 1977, and they've been going all that time, and they're finally taking pictures of all the planets, and they're out here, and they finally passed the area where it's out of the effect of the sun, past the heliopause. And so this is about the year, this is in 2014. These guys are about 125 astronomical units away. Now one more thing we're going to add here. Amazingly enough, we're going to put another comet path in. You can believe it. There are some very long period comets that reach all the way out to here. Put very long period comets. Now when the comets are out here, they're very small and they don't have tails. We can't even see them. We don't even really know where they are. We can't even really see them on a telescope. So you can put a dot if you want, or a couple dots to be the comets. Comets are just big fluffy snowballs floating in space, and they're not very large, so little white dots would be good things to represent them. So some very, very long period comets will come all the way out here. Now we're going to need to move the paper again, and we're going to have a big gap here. If we were going to make this to scale, we would have to make this space very, very large, many kilometers, many miles, hundreds probably. This is a very large gap here. Let's just draw an arrow and just put big gap. And we won't put anything in here. This will be empty to remind us it's a big gap. And now we're going to go to some very large distances. We're not going to measure in astronomical units anymore. We're going to measure in light years. 1 light year, and you can represent it LY, 1 light year is about 63,000 astronomical units. Remember back here we've been measuring, and these are very far out. The solar wind only goes out to 100 and 125 astronomical units. Now we're going to measure in light years, which are 63,000 astronomical units. Okay, so now we're going to be measuring in light years. So it's a lot easier to say 1 light year, or 2 light years, or 8 light years, or 100 light years, rather than if we kept measuring in astronomical units, we'd be talking about millions and billions of AUs, and it'd be a little harder to keep track of. So we're going to switch to light years. There's a big gap here of about on the order of 4 light years till you get to the first star. And we're going to put our star things on this last page. First of all, what's the closest star? Well, its name has the word close in it, Proxima, a little dot. It's called Proxima Centauri. It means the closest of the Centauri group. Now make 2 other dots real close to Proxima, and we can kind of put a circle around them. There's actually 3 stars that are so close they look to us like one star, and we call that Alpha Centauri. And Alpha Centauri is made up of Proxima Centauri, and then they call it Alpha Centauri. This one's called A and B. The other 2 are just called A and B. And this is approximately 4.2 light years away. So that's 268,000. It's the last time we use astronomical units. 268,000 AU away from us. Okay, so that's the closest star. You can write that if you want to. The closest star, it's famous for being the closest. Another star that's famous is the brightest star that we see. Now this is a little bit further away. Well, we can fit it right in here. Once again, it's actually 2 stars. I'm going to try 2 dots with a circle around it. But we call the star Sirius, and it's about 8.6 light years, and it's famous as the brightest star in our sky. Now I'm going to draw a line here. There's no lines, remember, actually, but in my mind it's kind of a dividing line. We've got the nearest star and the brightest star, and they're fairly close. And now we're going to talk about some stars that are much further away. And of course we can't talk about all the stars because there's thousands, millions of them, billions of them. Let's just talk about one constellation, just hitting the highlights here. Let's talk about Orion. Now Orion has 2 stars. I'll tell you the name of these stars. Let's put 2 stars here, and then Orion has 3 stars in his belt, 2 stars here, and then some little stars for his sword, and then 2 stars down here. And these are the only other named stars we're going to talk about. This one here is very famous. You may have heard of it. Betelgeuse. Some people call it Betelgeuse or Betelgeuse. It actually is a mistranslation of an Arabic word, Yod el Juza, and instead of the Bet El, they got mixed up. It was a Y. It was Yod, which means hand, El Juza, Al means the, and Juza was their word for Orion, so it would mean hand of Orion. But instead of Yod El, it got translated as Bet El for some reason. So Betelgeuse, it's about 245 light years away, and it's so large. It's 5 astronomical units in diameter. So the actual size of Betelgeuse is about the distance between the Earth and Jupiter. That's how large it is. This one has a neat name. This one's called Bellatrix. And it's about 640 light years away. This one down here is called Rigel, and it's about 720 light years away. And this one here is called Safe. It's an Arabic word, I think, and it's 650 light years about. So you can see these are not all in a plane. One's here, one's here, one's here. They're all spaced differently like this, but when we look at them, we see this pattern. And these here have names. This is Al-Nilak, Al-Nilan, Mintaka. These all have Arabic names, and if you want to add those names, you can look up Orion and on the internet, look out on Wikipedia, and you can write those names if you want to. But we're going to move on here. We're going to draw another line. So there's some stars that are about that far away. A lot of the stars and constellations that we see are about that far away. We've got 2 more little categories. This category, we're going to divide this kind of like a little stripe here. This category is what I think of as small weird things. Small weird things. And in this category, we're going to put black holes. Well, everybody's heard of black holes, right? And we can't, I don't know, black on black. We'll just have to kind of make a, well, it can't be black. We'll just have to make it white anyways. There, black hole. These are very small. These are only a couple miles, a couple kilometers across. But they're so dense, I think the star collapsed maybe, and it's got so much gravity, it's so dense, has so much gravity that not even light can escape, and that's why it's black. And there's a thing called a neutron star, made of nothing but neutrons, and once again it's really small, only a couple miles, couple kilometers across, maybe something like 10 kilometers across, and it's made of neutrons. It's very, very dense, not quite as dense as a black hole. Light can escape, but it is extremely dense, a lot of gravity, not much can escape. And there's something called a pulsar. It's kind of a type of a neutron star almost. Makes some light coming out from 2 sides. A pulsar is a neutron star that spins around. And if you can imagine that this is like a light beam coming out. Now we don't see it, you see it, don't see it, see it, and it like flashes. You can see the light's kind of reflecting. If I spin it very fast, it would almost look like when this handle passed, it would go flash, 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 and that's what happens with these. They spin around, and there's things streaming out like this, and as they spin, or like maybe a light on a police car or an ambulance when it spins around like that, or it flashes as it passes. This would be a good way to do it too. Flash, flash, like that, flash. And these can spin very quickly. They can spin like maybe 600 times a second, so they can really go fast. It's called a pulsar, means pulsating star. It kind of combines the 2 words. Okay, and the last category is really, really things that are large and far away. Large and far. We've got clusters of stars. 2 types of clusters. There's globular, and it's basically a glob. globular. The most famous one is just called M4, and M4 is about 7,000 light years away. A lot further away than our stars over here in Orion. And then there's some open clusters. The most famous is the Pleiades. They're open clusters. So we've got globular and open clusters of stars. Another thing we've got is nebula, or nebulae. The AE means plural. These are bunches of gas, means hydrogen and helium. And there's three kinds of nebula. There's something called planetary nebula, and has really nothing to do with planets. They thought that maybe planets might be forming in here, but so it's probably not true, but the name stuck. We're kind of stuck with it. But it's basically a star that's emitting a bunch of gas. So they're pretty circular. The most famous planetary nebula maybe is what they call the Cat's Eye Nebula. Then there are, put it in quotes here, planetary. Put this one in quotes, bright. There's bright and there's dark. Bright nebula, the most famous one might be, it's called the Flame Nebula, and this is basically just gases that are giving off light, and it's kind of cloud, like bright shiny clouds. Sometimes you see pictures of them, they're bright colors too. They're very beautiful. Dark nebula are places, the most famous one here we'll put is the Horsehead, where you see a dark shape. Horsehead kind of looks like this. You see a bunch of bright gas, and then there's a dark shape in the middle, and the dark shape is like a cloud of gas that is blocking the light from this other gas, and so you get kind of a silhouette. The Horsehead Nebula, and I believe maybe the Crab Nebula is also in this category. So you've got planetary, bright and dark nebula, and the last thing is the galaxies, which are just huge groups of stars, billions of stars. And you have elliptical and you have spiral with some arms coming off. And then you can have clusters of galaxies and things like that. But that's a pretty good summary of what's out there. Here's a little trick for storing it. If you want to fold it up, which I assume you probably will, it'll fold into 3. But it might fold a little bit better. You'll find it's kind of maybe a little bit puffy. If you trim just a little tiny bit off one end, this will give you just that little bit of leeway right here, so it'll fold nice and flat, and you can just stick it into a portfolio or a binder or something.